So, what if I told you that you could double a large language model's logic and math accuracy tonight?
Like completely without touching a single weight.
Exactly. No fine-tuning, no retraining, nothing. Look, if you're tuning in right now and you're maybe staring at your IDE in a dark room.
Trying to unblock an architecture issue while the rest of the house is asleep.
Yeah, we've all been there. Well, this deep dive is specifically for you. Our mission today is exploring this wild technique from the LLM Mastery series.
Oh, right. Self-consistency.
Yes, self-consistency, which, I mean, it's an architectural pattern applied entirely at the prompt layer. It essentially gives you a way to squeeze state-of-the-art performance out of off-the-shelf models.
Just by changing how you ask the question.
Mm-hmm.
And, well, how you process the answer.
Exactly. It's a massive operational win because, you avoid all that brittleness.
And the expense, yeah. Creating those massive custom data sets for fine-tuning is a nightmare.
It really is. So the core mechanism here is taking a standard chain of thought prompt where you tell the model to think step by step before answering.
Right, but you run it in parallel.
Yes. Instead of asking the model to generate one single reasoning path, you generate several distinct reasoning paths for the exact same prompt.
And then you just take the final answers from all of those generations and use a simple majority vote to figure out the correct output.
But wait, I need to clarify how that actually improves accuracy. Because, I mean, we are dealing with probabilistic engines here.
Yeah, very probabilistic.
If you ask an LLM to solve a complex logic problem or extract some nuanced data multiple times, it's going to take slightly different routes to get to the answer.
Definitely. And some of those routes are going to include hallucinations.
Right. It might drop a carry in a math problem or, I don't know, misinterpret a variable midway through its reasoning.
But see, those localized errors are exactly why you need multiple paths. Different reasoning attempts will naturally make different, completely isolated mistakes.
Oh, interesting.
Yeah. So the central truth of the logic, like the actual correct answer, will typically appear most often across all those different generations.
Even if the individual paths the model took to get there vary wildly.
Exactly. And this isn't just a hunch. It's mathematically grounded in the Condorcet Jury Theorem.
The Condorcet?
Jury Theorem. It's an idea from political science dating back to the 1700s.
Wow. Okay. We're going way back.
Yeah. The Marquis de Condorcet proved that if you have a group of voters and each individual voter has a greater than 50% chance of being right about a binary decision.
Okay, greater than 50%.
Right. If you add more voters to the group, it actually increases the probability that the majority vote will be correct. As the group gets larger, the probability of the majority being right approaches 100%.
Let me pause you right there because the math implies a pretty massive caveat.
The baseline probability.
Yeah. The theorem only works if the baseline probability is greater than 50%.
Right.
If the underlying model is fundamentally bad at the task you're asking it to do, meaning it has like less than a 50% chance of getting it right on the first try.
Then adding more voters would actually accelerate the failure.
Exactly. A majority vote in that scenario just mathematically guarantees you get the wrong answer.
Which is a really critical boundary condition to keep in mind. I mean, self-consistency is not a magic wand for a model that doesn't understand the domain at all.
Right. It needs baseline competence.
Yeah. Assuming it has that competence, the consensus effectively filters out the individual stochastic errors in its reasoning.
You know, it reminds me of daily life managing a software engineering team.
Oh, yeah. How so?
It's like asking 5 independent senior devs to debug a complex distributed system. If you just ask one, they might figure it out or, they might go completely down a rabbit hole.
Looking at DNS logs when it's obviously a database log.
Yes,
yeah.
Always the DNS logs. But if you put 5 independent devs on the problem, they take different diagnostic paths. One traces network packets, another profiles the database.
And maybe 2 still end up in the DNS rabbit hole.
Exactly. But if 3 out of those 5 completely independent diagnostic paths arrive at the exact same root cause, say a deadlocked transaction on table X, you confidently merge the FEX.
The consensus strips away the individual diagnostic noise. That's a great way to look at it. But the operative word in your analogy is independent.
Right.
For that team of developers to be effective, they cannot be looking over each other's shoulders.
Right, because if developer number 1 says, I think it's DNS, and the other 4 just nod and agree.
Your majority vote is completely useless. You've just amplified the initial error.
Which introduces an obvious technical friction point here.
The determinism of the model.
Yes. An LLM is a deterministic machine at its core. If you pass the exact same prompt to the exact same API endpoint 5 times, you would intuitively expect the exact same output 5 times.
So how do we force the model to take different reasoning paths?
Yeah, how do we...
We engineer that independence through system parameters,
Mm.
specifically by adjusting the temperature.
Ah, temperature.
Right. Temperature alters the probability distribution of the next token the model selects. A lower temperature sharpens the distribution, heavily favoring the most mathematically probable next word.
And a higher temperature flattens that distribution, making less likely tokens more probable.
Exactly.
So let's push back on the extremes to illustrate this for the engineers listening. Say we set the temperature to 0.0 to guarantee a deterministic output. What happens when we trigger our multiple reasoning paths?
At a temperature of 0, the model picks the exact same sequence of highest probability tokens every single time.
So you pay for 5 generations, but you get 5 identical chains of thought.
Yeah. It's the equivalent of a sample size of 1. Your majority vote is just a consensus of clones.
Totally useless. Okay, then consider the opposite end of the spectrum. We crank the temperature up to like 1.5 or 2.0. We want maximum diversity.
At that point, the probability distribution is so flat that the model starts picking highly improbable words at random.
So you get completely incoherent hallucinations.
Yeah, the model loses its ability to maintain a logical chain of thought because it is constantly taking these wild semantic leaps.
Right, so the developers aren't debugging anymore. They're writing abstract poetry about the database.
Exactly. Which is why the source material explicitly calls out a sweet spot for self-consistency.
What's the range?
It suggests a temperature setting between 0.5 and 0.8.
Okay, so we're trying to dial in just enough variance to force the model to explore different logical routes without, losing the plot entirely.
Because engineering self-consistency is fundamentally about engineering diversity. That temperature dial turns a single static LLM into your dynamic team of independent developers.
It's kind of a paradigm shift.
It really is. Normally, when we want a factual, logical answer like solving a math equation or parsing a document, we set the temperature to 0. We're taught that 0 equals facts, and higher temperatures equal creativity.
But here we're using a controlled amount of randomness to actually improve the logical rigidity of the final answer.
We are using chaos to reveal the most stable underlying pattern.
I mean, I buy the theory. Using controlled chaos to find truth is a great concept. But as an engineer looking at my architecture diagram right now, the immediate red flag is the cost.
Oh, for sure. The compute cost is real.
Yeah, the sources are very transparent that running this technique creates an n times compute cost. If I want a majority vote of 10, I'm generating 10 times the tokens.
That adds up fast.
For anyone managing a startup's runway or an enterprise latency budget, running a chain of thought prompt 10 times in sequence means the user is staring at a loading spinner for a minute.
And your API bill is going to be astronomical.
Right. So how do we practically build this?
Well, we have to implement specific architectural mitigations to deploy this in production. The first mitigation directly solves the loading spinner issue.
Parallel generation.
Exactly.
Yeah.
Because LLM APIs are stateless, you don't wait for path 1 to finish before starting path 2. You fire off all your requests concurrently as asynchronous calls.
Oh, nice. So the total latency becomes just the latency of the single longest generation.
Plus a few milliseconds of overhead for your voting logic, yeah.
But wait, parallel generation sounds great until you hit your AP provider's rate limits.
Yeah, that is the catch.
Firing off 10 concurrent requests per user action is a fast track to getting an HTTP 429 too many requests error.
Which means anyone building this needs to implement robust retry logic, exponential backoff, jitter.
Or if you're operating at scale, you might need to load balance those parallel requests across multiple API endpoints or even different cloud regions.
Managing concurrency limits is definitely the operational hurdle there.
Yeah.
But even once you solve the latency problem with concurrency, you're still left with the financial problem.
Right, because you're still paying for every single token across all those concurrent streams.
Exactly.
Well, if we're treating this like a literal election, I imagine we don't always need to wait for every single precinct to report, right?
What do you mean?
Like, if one answer gets an insurmountable mathematical lead early on, couldn't we just sever the remaining API connections to save money?
Yes. That is the second mitigation. Early stopping.
Okay. How does that work?
You implement a dynamic threshold in your application layer. So if your target is a majority out of 10 paths, you fire off 10 parallel requests. As those asynchronous streams return their final answers, your application tallies the votes.
And if the first 6 all return the exact same output,
Mathematically, the remaining 4 cannot change the outcome.
So at that exact moment, you drop the remaining network requests midstream.
You literally stop the generation and cap your token expenditure.
That's brilliant. But there's a glaring implementation detail missing here.
Which is?
How exactly do we tally those votes programmatically? Because the output of a chain of thought prompt isn't a neat integer. It's like 3 paragraphs of unstructured reasoning.
Right, it's this very messy text.
We can't just run a simple string comparison. Model 1 might say the final cost is $42, and Model 2 might say, therefore, $42 is the total.
Yeah, you need a structured extraction mechanism. The most robust way to handle this is to instruct the model in your initial prompt to wrap its final conclusion in specific XML tags.
Oh, okay. So you tell it, think step by step, and then place your final answer inside answer tags.
Exactly. Then your application just runs a simple regular expression to pull the contents of those tags.
And then you normalize the extracted strings, maybe stripping white space, lowercasing it, and run your frequency count.
Right. Alternatively, some architectures use a very cheap high-speed model, like Claude Haiku or GPT-4o Mini, purely as an evaluator.
Oh, that's clever.
You pass the 10 unstructured outputs to the mini model and ask it to group the matching conclusions. It adds a tiny bit of latency, sure, but it handles semantic similarities that a regex would totally miss.
Okay, so we've mitigated latency with parallel calls, and we've mitigated token costs with our early stopping.
Yep.
But even with those tricks, running self-consistency on every single prompt feels like overkill. Like, if I have a routing layer in my application that just needs to decide if an incoming email is a support ticket or a sales inquiry.
A single zero temperature call is going to be 99% accurate anyway. You don't need a Joy to tell you that 1 + 1 = 2. This brings us to the third and most sophisticated architectural pattern, cascading.
Cascading. Okay, what's the principle there?
The principle of cascading is that you reserve the expensive, heavy machinery of self-consistency only for the edge cases that actually require it.
So you trigger the multipath voting mechanism strictly when the model's initial confidence is low.
Exactly.
But wait, you say when confidence is low, but you can't just ask an LLM, are you sure about that?
Oh, definitely not.
Language models are notorious people pleasers. It will just hallucinate absolute certainty and tell you it is 100% confident, even when it's completely wrong.
Right. You do not ask the model to self-evaluate. You look at the log probs.
The log probs.
Yeah, most major LLM APIs allow you to request log probabilities, the actual mathematical probability the model assigned to the tokens it chose.
Oh, right. And those are typically returned as negative float values, right?
Yeah.
Yes.
Where a number very close to 0 indicates near absolute certainty, and a more negative number indicates the model was choosing between several competing tokens.
So the cascading architecture works by firing a single standard request first.
Exactly.
Then your application inspects the log prob of the specific token inside that answer tag we talked about earlier. If the log prob is high, say Natch is 0.01, your app accepts the answer and moves on.
And that transaction costs a fraction of a cent.
But if the log prob dips below a threshold you've defined, meaning the model was mathematically uncertain about its conclusion, your application catches that flag.
It discards the initial answer and gracefully degrades into the self-consistency loop.
Automatically firing off the multiple parallel paths to get a more robust debated answer. That is so cool.
Right. You get the speed and low cost of a single prompt 90% of the time, and the deep accuracy of a majority vote for the 10% of complex edge cases that would normally break your pipeline.
It really transitions this concept from a neat academic paper into a highly resilient, deployable production pattern.
And establishing those thresholds requires profiling your specific data, but the architectural pattern is universally applicable.
Which naturally leads us to knowing where in your application stack this tool actually belongs.
The sources draw a very clear use case boundary here. Self-consistency provides a massive lift for problems that have definitive, verifiable right answers.
So we are talking about domains where a ground truth exists. Math equations, logic puzzles, complex data extraction, routing decisions, code vulnerability analysis.
The technique fundamentally relies on the premise that the correct answer is a single point of convergence.
Which means the inverse is equally important.
Oh, absolutely. Self-consistency helps the least and can actually be detrimental for open-ended or creative tasks.
That tracks perfectly with our senior developer analogy. You want a majority vote of 5 devs on whether a database schema will scale, because there is a right and wrong answer dictated by the laws of computing.
Right.
You absolutely do not want a majority vote from 5 devs on how to write engaging marketing copy or a creative story.
Because by trying to find the majority vote in a creative task, You are enforcing consensus regression.
Consensus regression.
Yeah. If you ask 5 different language models to write a poem and then try to extract the most common themes or phrases among them, you strip away every unique, eccentric, interesting choice the models made.
Consensus in art usually just means boring.
Exactly. You mathematically enforce mediocrity.
You end up with the most vanilla output imaginable because the correct answer in a creative task isn't a point of convergence. It's the novel outlier.
So when you are architecting AI features, you have to categorize your LLM calls based on this boundary. Developers should reserve self-consistency exclusively for the unseen infrastructure of the app.
Use it when the LLM is acting as a reasoning engine, a classifier, or a parser. Avoid it when the model is acting as a creative collaborator.
Precisely.
But this highlights a crucial reality of building with LLMs right now. Getting the model to produce the correct logical answer is really only half the battle.
Yeah, if we're using self-consistency in the hidden infrastructure of our apps, we almost certainly need those answers in a format that the rest of our deterministic code can actually read.
Right. If the model wraps its perfectly reasoned, consensus-backed answer in 3 paragraphs of friendly text saying, "Certainly, I'd be happy to help you extract this data,"
Your application's JSON parser is going to immediately crash.
which segues perfectly into the subject of tomorrow's deep dive. We are going to tackle structured output.
Oh, that's a big one.
We'll look at the engineering patterns required to force these probabilistic models to output perfectly parsable data, like JSON, XML, and executable code reliably every single time. Structured output is really where prompt engineering merges with traditional software engineering.
It is the necessary bridge to make language models play nicely with the rest of your deterministic stack. I mean, once you have the accurate answer through self-consistency, structured output ensures you can actually use it.
I am incredibly excited to unpack that tomorrow, but let's recap what we've covered tonight for everyone out there still reviewing pull
Let's
requests.
do it.
The TLDR self-consistency is a powerful architectural pattern that leverages the Condorcet Jury Theorem. By generating multiple reasoning paths and taking a majority vote, you can significantly boost a model's accuracy on logical tasks.
And you enable this by tuning the temperature, usually sitting in that 0.5 to 0.8 sweet spot, introducing just enough diversity into the model's generation to explore different paths without degrading into hallucinations.
And you manage the inevitable n times compute cost by utilizing asynchronous parallel generation with proper rate limit handling. You implement early stopping using regex extraction to kill redundant requests.
And you build cascading architectures that trigger the jury only when log probs indicate the model is actually uncertain.
It is a phenomenal practical tool for the rigid layers of your software stack.
Before you get back to your code, though, consider the philosophical implication of this architecture.
Okay, hit me.
We spend so much time trying to engineer out the flaws in these models, right? Trying to prevent them from making errors. But if the ultimate truth derived from an AI in this system is simply the mathematical consensus of its own diverse and sometimes flawed reasoning paths,
Yeah.
perhaps making a model smarter isn't necessarily about teaching it not to make mistakes.
Wow. Perhaps true intelligence, at least when deploying these probabilistic systems, is simply giving the architecture the space to outvote its own errors.
Exactly. It is not about perfect generation. It is about perfect selection.
We're going to leave you with that thought to chew on. Keep tinkering, keep building, and hopefully all your integration tests pass on the first try tonight. We'll see you tomorrow for our deep dive into structured output.